Hello again, welcome to another presentation. This time we're going to look at permittivity, permeability, Maxwell's equations, and also the possibility of a magnetic monopole. Okay, so starting off very lightly into the permittivity of free space. Now starting from Coulomb's law, which is the concept that alike charges repel and unlike charges attract. This is electrostatics. So you see electric force acting on a point charge Q1 given by Coulomb's law, like charges repel, unlike charges attract. F equals KQ1 Q2, the product of the two charges divided by the square of the distance between them. And K in this case replaced by 1 over 4 pi epsilon naught. So that's Coulomb's law. And E naught, epsilon naught here, is the permittivity of free space. Now this image here is taken from a very helpful website called Hyperphysics, and it satisfies Newton's third law of F equals ma, and you have this inverse square law, and K is 1 over 4 pi epsilon naught, roughly equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Epsilon naught here is the constant 8.854 times 10 to the minus 12 farad per meter. F equals 1 over 4 pi epsilon naught, the product of Q1 Q2 from here, where K equals 1 over 4 pi epsilon naught. Now epsilon naught equals Q1, when you rearrange it, Q1 Q2 over 4 pi FR squared. Q equals the current, the charge is the current times time, which is measured in amp second. So if we substitute in the units there, so the Q's, the two Q's multiplied by each other give Coulomb squared. The 4 pi of course has no units, force is measured in newtons, and R squared is meter squared, and we know that a Coulomb squared is an amp squared second squared, divided by Newton meter squared comes up with the final units here. Intermediate units, you can go to the end of the world on these units, but I'm keeping it in the terms of amp squared second squared per Newton meter squared. And the reason for that, which will come hopefully in the next one. Then we have the permeability of free space, where we have mu naught is 4 pi times 10 to the minus 7 Henry per meter, and permeability is to do with magnetism, permittivity to do with electrostatics. And here we have slightly more complicated equation. It is a vector equation. The dB is mu naught I over 4 pi r squared dl cross L hat, the unit vector L hat. If we get rid of the unit vector because it's purely just a number, rearrange in terms of mu naught, you have 4 pi r squared over I dB by dl. Now of course force is QVB, which is charge times velocity times magnetic field, which means that the B is the force divided by charge times the speed. So the force is measured in Newton, charge is measured in Coulomb, speed is meters per second. Put it into that equation, so you have mu naught equals 4 pi r squared over I dB by dl is, of course, 4 pi has no units, r squared is meter squared, I is measured in amps, and dB by dl, you're just going to put that in there instead. And of course you've got an L here, so you need to divide by 1 meter. So that one is the dB, and that is the dl. And then as we work the equation through, you have meter squared Newton over amp Coulomb meter squared per second. And mu naught is measured in Newton amp Coulomb per second when you cancel the meter squared. Of course, they've done before, charge is IT, which is measured in amp second. And then you put that into that part there, and you end up with mu naught is Newton over amp squared, because the per seconds cancel out. So the units of magnitude, you have mu naught E naught. So what happens if I multiply the permeability of free space by the permittivity? We have Newton over amp squared multiplied by the permittivity amp squared second squared over Newton meter squared. And of course the newtons cancel and the amp squared cancel, and you end up with second squared per meter squared, which just rearrange it in terms of meters per second, meter to minus 2 times second squared. The speed of light squared is one reciprocal of the product of these two, so 1 over mu naught E naught. So therefore, then mu naught E naught is 1 over c squared. Now c squared, of course, speed of light. Speed is measured in meters per second. You square that, you get meters squared per second squared. And then if you just invert it, you put a 1 over, you have 1 over meters squared, and you end up 1 over mu naught E naught. And then multiply that, those are units. The units actually work out very nicely because that's what I'm looking for. Meters minus 2 second squared. I've just inverted that, so that's exactly what I'm looking for. Look at the values, the magnitude. Mu naught is 4 pi times 10 to the minus 7. E naught is 8.854 times 10 to the minus 12. Multiply them together. Take the 1 over, end up with 8.988 times 10 to 16. If I then take C as 2.998, it's roughly 3 times 10 to the 8. If I square that, I then end up with the same answer. So the units of per meter squared second squared of mu naught E naught are the same as c squared, and the value is the same as well. Which is really interesting because you multiply permittivity of free space, which is electrostatics, multiplied by the permeability of free space, which is magnetostatics. For want of a better term, you end up with 1 over c squared, the speed of light squared. Then we get into the 4 Maxwell equations. Again, these are taken from hyperphysics. You have the integral form, integral of EDA, etc. Integral form, which is quite helpful to start off with, but much more commonly used are the differential forms. So these are 4 equations which basically say that you have electricity here, magnetism here, induction, Ampere's law, and then you have Gauss's law from electricity, magnetism, Faraday's law, and Ampere's law. So you've got the same type, but you've got slightly more complicated bits here. But you see you've got c squared as 1 over mu naught E naught. Let's break this one down. They're handy, these two are handy, but they're not as easy to follow, I think, anyway. How do I do it? Well, I have them simply set up here. Your divergence of the E field, so do they diverge together? Yes, they do. So you have a charge here, for example, that's going to be a plus charge, and the end of it, you can have a negative charge, and they have a diverging field, which means they go to a point, which is what you have a point charge in electrostatics, and it is the diversion of the field is to do with the density divided by the medium which it's in. So of course we're talking electrostatics, so it has a diverging point, and it is dependent upon the density and the electric field component, the permittivity of free space. That's a visual representation of the divergence of an electric field. The divergence of a magnetic field is 0, that is the pictorial representation. So these magnetic field lines do not diverge like here. They do not come to a point as far as we know, but as far as we can measure. So that is the conclusion, the pictorial representation of a non-diverging electric field. The curl is just something changing with respect to time. So you have the curl of an E field, which changes with the minus the spatial curl, because that's the spatial curl, is a minus time differential of the magnetic field. So you've got this one here, you've got like water going down a plug hole kind of mentality. So you have it's moving around as it's changing with time. And then you've got the spatial curl of a B field. Now you have a mu naught, which is the permeability with the current density, and then you have either mu naught E naught or 1 over c squared, and the rate of change of the E field. So it's probably going to be best represented by that image there. It looks complicated, but it does bear sense when you look at the actual pictorial representations. Now I'm going to show a quick clip from the Big Bang Theory when I talk about a magnetic monopole.
Sheldon, you remember the first few weeks we were looking for magnetic monopoles and not finding anything, and
If there were such things as a magnetic monopole, well, what would happen there would be, for example, here we have the PBS image here, it's quite nice actually. This exists, a north pole with the field lines going round to the south pole, and this should exist. We have a north pole as a point and then the field lines going out from the north pole. So if it did exist, then using c squared as 1 over mu naught E naught, then mu naught is 1 over c squared 1 over E naught, and E naught is 1 over c squared 1 over mu naught. And of course c squared is a constant, so we can just say the proportional. So mu naught is proportional to 1 over E naught, and E naught is proportional to 1 over mu naught. So inverse proportion. So with that bearing in mind, given that as it stands Maxwell equations are the divergence of the E field is rho over epsilon naught, and the divergence of the B field is 0, if there were such thing as a magnetic monopole, then there'd be beautiful symmetry, because you'd have that would be unchanged, but you'd have the magnetic, rho magnetic, and E naught as a divider here. You then have this as a multiplier here. So there's a beautiful symmetry there. Similarly, you have the curl of the E field, which is minus dB by dt, and then the curl of the B field, which is all this. Then if there were such thing, then of course, then you'd have the reciprocal of this. So you have 1 over E naught instead of mu naught J mag, and then probably a minus sign 1 over U naught E naught dB by dt, because you've got the minus sign here, and then you have that factor in front of the time, and then that one would be unchanged. So you see, it's interesting that you have the case of the divergence of the E field is unchanged, the B field, the divergence of the B changes, and here we have potentially, it's just a theory out here, the curl of the E field will change, would possibly change, and the B field will stay, the curl of the B field will stay the same. Theorized, but there's beauty with this. You see, that's why there's such a search for the magnetic monopole, because it would bring symmetry to Maxwell's equations. And this is just out of a thought there, that the magnetic field in the flat earth, on a so-called flat earth, is that there's a point here at which all the north lines go out from the central point of the actual map. And that may indicate there's a magnetic monopole, who knows. What is very interesting is that very image is replicated by all these international organizations, and it's called the azimuthal equidistant projection. So there's quite a few that use this layout as whether or not that is actually the case. You have a simple magnetic pole here, and the outside is a south pole. The permeability, again, that's permeability of free space. We've got the magnetic field, that's how it looks. The wires go through in a solenoid, a bar magnet, and this is the globe model of the Earth, and that's a Biot-Savart law, which is where we get the dB by dL. That's to find that one. So that's an introduction into permittivity, permittivity, Maxwell's equations, and a magnetic monopole. I hope that's been useful, and these are the references to have a look at. Thank you.